Let's say the generic equation is known, okay, because of both the stream function and the velocity potential in U and also in V. Okay, so the next thing we should know actually is our source and our sink. Okay, so source and sink, okay, actually it's the same thing. Okay, so the difference between two of them, right, is that the direction is different. One is radiating outwards. Okay, one is going into a certain source, into a certain point. Okay, so it's just a plus and a minus, that's all. Okay, because of the direction. Alright, so you can notice from here, okay, the only component that I'm concerned about is my VR. Okay, there's no V theta. Okay, later you'll see that V theta because it's tangential. Okay, and because both the source and sink is not rotating. Okay, so your V theta will be equal to 0. Alright, so you can imagine that these are actually radiating outwards, that's all. Okay, so flow will just go uniformly, okay, either inward or upward, okay, depending on the values that you see. So in polar coordinates, okay, please remember these two very important points. Okay, your v theta is 0, and therefore, right, the total velocity will just be equal to vr. Okay. Okay, so your v theta is your square root of v theta squared plus vr squared by definition. Okay, it just happens to be equal to vr because your v theta is 0. Right, so that's why the square root of vr squared will just be your vr. Understand? Okay, but if right, I got a flow that's superimposed together, that means I got a uniform flow plus a source flow or sink flow. Okay, I cannot assume that the v theta is 0. Understand? Okay, so just for individual flow, then we can assume that this is equal to 0. Right? Can I move on? Okay, so for a source and a sink, okay, we have, unfortunately, we can only use our polar coordinates to represent the flow. Why? The reason is because it's actually in a circulation or a circular flow form. Alright, so we can only use r and theta as our coordinate system here. Okay? So again, right, for us at this point of time, we are assuming that it's an incompressible flow. Okay, so when it's an incompressible flow, okay, the divergence of the vector field should be equal to 0. Okay, this is what I've given to you, I think on slide 3 or 4, okay, as a value already. Okay? So, the more important thing is this, okay, it's irrotational at every point. That means your v theta equals to 0. Okay, so a sink flow is just basically a negative source flow if you like. Right? Okay, so we have derived the uniform flow in terms of stream function and velocity potential in both Cartesian and polar coordinates form. Alright, so we can do the same thing now for our source and our sink. Alright, so let's consider now a source. Okay, so how do we actually find out the values that we have? So the best way for us to do it, right, is still by the conservation principle. Okay, so when we talk about conservation principle, right, the first conservation is conservation of mass. Right, so what's the formula for conservation of mass? Anyone? Can you remember? M dot equals what? The first equation that you should always remember is this: M dot is always equal to rho UA. Okay, this first equation, no excuse. Every one of you, right, have to know this equation here. Okay, mass flow rate. M dot is your dm dt. Right, that means the rate of change of mass with respect to time. Okay, so it's kilograms per second. That's our mass flow rate. Okay, what is your rho here? What is your u? Velocity, right? And what's your a? Area. Very good. Okay, so now if I want to put this equation, this is a conservation equation, okay, into a source equation, into a source flow. Okay, the rho will never change. Okay, but my u, right, if I want to write it more specifically, I should write it as vr. Okay, why? Because that's v theta equals to 0. The only velocity component that I have in this flow here is really my vr. That's why I put as vr. Okay, now the area, right, okay, is one that I think you need to understand. If I'm a flow, okay, what do? I'm actually radiating outwards along the circumference of the circle here. Alright? So if I want to know as an area, right, area is length times breadth, right? But to me, right, the length or the circumference is actually what I'm seeing as a flow, right? What I see right is that my circle is getting bigger and bigger and bigger. So that's why I got a 2 pi r here. Alright? Now what is my L? L is just an assumed depth of the source. Because area must be two-dimensional, right? Okay, so to me, right, is that if you can imagine this, right, to be going into the paper, okay, with a certain depth L. Okay, that's why it's 2 pi r L here. Okay? Now let me give you another example. If, right, okay, if I have a flow, right, if I just draw this here, with a flow that's going, let's say this is an aircraft body. Okay, so at the start, we can assume that this is a spherical shape, for example. Okay, so right, if I want to go past this solid body, right, okay, the area that I see, right, if I have a flow, what do I see? I see a sphere in front of me, right? So the surface area of a sphere, right, is not 2 pi r anymore. The surface area of the sphere is 4 pi r squared. So my A, right, will become 4 pi r squared. Okay? It's the same thing. If I now give you a rectangular block here, that means if I face the rectangular surface, right, or the surface of a rectangular block, okay, then the area will be the surface of the rectangular block. Okay, so for this case, right, because I'm looking at this as my circle goes bigger and bigger, okay, the change is my r. So it's just changing from 2 pi r, which is my circumference, multiplied by L, which is then will give me an area. Okay, so if you do from a dimensional point of view, right, okay, r is in meters, L is in meters also. So if you take meters per meter, right, you get meters squared. Okay, so that's the dimension for A already. 2 pi is just your constant, so there's no dimensions involved. Okay, so this definition doesn't change. M dot equals rho A doesn't change. But what we put in, right, depends on the question. Okay, so if you see some past year papers, right, they say a flow is going past a spherical shape, for example. Some students, right, just memorize this and just put 2 pi r L. Okay, they get the wrong answer already because the area is not correct. Okay, so the area roughly should be 4 pi r squared. Alright, okay, so just think of this. Okay, we'll come back to this again. Okay, as we go through some exam papers. But I just need you to understand the difference. Okay, don't take this as for granted or it's the same for every question that you see. Okay, this is only pertinent, okay, to this example here. Are we all good with this? Okay. Okay, so we have this mass flow rate already. Okay, so but we still cannot get our values, I mean the stream function and the velocity potential that we want. Okay, so there's something else that we can do. Okay, the other thing we can do, right, is actually to find out the volume flow rate. Okay, because density is mass over volume. Okay, so we can actually find, if you know the mass flow rate, okay, rightfully you can also find the volume flow rate. Okay, it's just really divided by density, that's all. Okay, can you understand where this? Okay, this equation is from the definition of density is mass over volume. Okay, that's why volume is mass over density. Okay. So instead of writing my equation in terms of mass flow rate, okay, I can just change this now into an equation that is volume flow rate. Okay, what's the difference between these two? It's just the density that's divided, that's all. Okay, what you can do, right, is to further divide the volume flow rate per unit length. Okay, because L, right, is the length that we assume. Alright, so if I want to have my equation that's irregardless of the length, okay, I do it as per unit length. So it's V dot over L here. Okay, so I just get my 2 pi r times my radial velocity. Okay, so you can see, right, what I do is that even though I assume an arbitrary value of L, at the end of the day, right, I still divide by this L here. So I'll get rid of this L here. Alright. So there's a definition for V dot over L, right? So V dot over L, okay, is always has this symbol here. Okay, it's a inverted V if you like. Okay, but what this symbol means, right, it just tells us that it's the source strength. Okay, that means the strength of the source that we have. Or if you want, if it's negative, right, okay, it just represents the sink strength, that's all. Okay, so what you can write down, right, is this. Your radial velocity is equals to the source strength divided by the radial 2 pi r. VR, that is the circumference of where the source is. So this is a very important equation because this tells me, right, as my circle gets bigger and bigger and bigger, right, what happens to my VR? Smaller and smaller and smaller, right? So this is the same, right? If you have, it's the same example, if you draw a pebble into a pond, as the circle gets bigger and bigger, right, the strength gets smaller and smaller. So the radial velocity gets smaller and smaller. So you dissipate away the energy, right? So this is correct. Okay. So this is very important because now if I know my VR, okay, that means what? I can find my velocity potential and my stream function already, right? Okay, so v theta again, right, is equal to 0, okay, because it's still rotational. Alright, so the units for source strength anyway, if you want to know, is meter square per second.
The one I said just now is this one, copy or not?
Because volume flow rate is meters cubed per second. Meters cubed per second divided by meters, right, you get meters square per second. Alright, so there's a source strength or the sink strength, depending on the positive or negative. Okay, so now we can do the same thing that we have done for my uniform flow. Okay, I can get both my stream function and my velocity potential. Alright, how do I do that? Okay, I need these equations here. Okay, my VR and my v theta. But it's simple because my v theta is equal to 0 for this case. Okay, but this is sufficient enough for us to find the stream function and velocity potential rate. Okay, so for stream function, it's quite simple. Okay, VR equals to my source strength over 2 pi r, which is equals to 1 over r delta psi over delta theta. So I can then do what? How do I find stream function? I can integrate, right? Okay, so if I integrate this, okay, I get my stream function equals to the source strength times theta over 2 pi. Okay, so I must also do my v theta, okay, just to complete the math. Okay, but it just happen that it's equals to 0, right? Because tangential velocity equals to 0. Okay, so we'll get the answer for this already. Any to copy here? I think is it. Okay, so we can do the same thing for our velocity potential. Okay, so what do we use? Again, we can use this equation here, correct? Okay, so for velocity potential, okay, we know by definition Vr or your radial velocity is del phi over del r. Okay, and then we have the definition for Vr. Okay, this is quite easy to do. Okay, so we want to find your velocity potential. You will get ln r. Okay, anyone got any problem from this second line to the line? Understand how can I get ln here? Can, right? Because this is one of your source strength is constant, your 2 pi is constant. Basically, I'm just integrating 1 over r dr. So I get my ln r here. Okay, okay, again, your v theta equals to 0. Okay. Yes. Yes. What will it be? Okay, theta. Okay, see, right? Let's say if I have a source, right? I have a source, right? My velocity is going in this direction. So if you think about it, right? V theta is 0 because the flow is not moving in any circulatory motion, right? But what is theta? Theta represents, let's say if I want to find at this location, what's my VI equals to, for example, right? So I can find this is my theta. So theta is your displacement. Yeah, it's your angular displacement. It's different from V theta. Okay. So let me get back to this. So now I have my velocity potential and my stream function, right, in terms of my polar coordinates, right? So if we still want to insist on putting back into Cartesian, we can do that. Okay, so let me just go back to the previous slide first. Okay, your stream function is what? Source strength times theta over 2 pi. Okay, your velocity potential is source strength over 2 pi times ln r. Okay, now what is r equals to, remember? How is r related to x and y? Anyone remember? Square root x squared plus y squared. How is theta related to x and y? Theta is equals what? Tangent inverse of y over x, correct? Okay, so if you can still remember the relationship between my polar and my Cartesian, okay, if you still insist on putting in Cartesian, these are the two values that we will have. Okay. I think there's something to copy, right? So this is for source and sink. Okay, so what I've done for you, right, is again to come up with these two these two equations for you, whether it's a polar or Cartesian form. Okay, but basically, right, is this because we talk about the Laplace equation, right, we can actually superimpose the stream function and velocity potential together. So if I want to add my uniform flow to a source or a sink, okay, I need to have this definition here so I can add up the stream functions. Okay, then I'll show it to you also. Okay, so just remember, okay, for sink, right, it just means your inverted triangle here is just a negative value. Okay, your phi and your psi will have the same definition. Okay, just that there's a negative sign in front. Okay, so this is just telling us that look at the arrow. So in the questions, right, it doesn't tell you whether it's the source and the sink. Okay, it will indicate through the diagram that you see. Okay, so just be mindful of the values that you see here. Okay, so we went through uniform flow. We have your source with your sink. The next one that's important, right, actually is your doublet. Right, so what's a doublet? Doublet is just really, right, where you have your source and the sink that is a pair together. Okay, but they are very, very close together. Okay, so let's try to define what is this doublet value that we're looking for. Okay, so take note of a few things. I must have a distance L. Okay, arbitrary value again. Okay, that means it's a distance between the two points, the source and the sink. Okay, I must also have this here. This is your strength. Whether it's your source strength or sink strength, okay, it's a value that you must have. Okay, so let's, for example, right, I have a source and a sink. Okay, separated by a certain length L here. Okay, I want to find the stream function. Okay, at a point P here. Okay, how do I do that? Okay, so remember what I talked about the superposition, right? Okay, meaning to say, right, this point P here is affected by both the source and also by the sink, right? So let's say if I put a certain probe here, okay, to measure the velocity or pressure, okay, this value that I measure, right, must be because of both the source and the sink that we have. Okay, if it's too far apart, right, okay, then obviously this is independent of these two. It's not a doublet anymore. But the thing is, right, when it's too close together, okay, then you can then consider this as doublet flow. Alright. So how to do that, right? It's just really just this. If I want to find the stream function at point P, okay, as I said, right, it must be because of both the source and the sink. Okay, so I must add these two up. Okay, now when I add these two up, right, you realize that because what the source is a positive value, the sink is a negative value, okay, I will have a negative value here. I see. You understand what I'm saying? Yes or no? Okay, because for a source, right, okay, if you remember the formula is your source strength times your theta over 2 pi. Alright? Now if it's a sink flow, right, it has to be a negative of your source sink strength times theta over 2 pi. Now if I add both together, right, obviously the negative sign will be just here. Because this strength over 2 pi is a constant value. Right? So what is changing is just the negative sign that we see. Okay? So either I write this, okay, in this form here, okay, or I can write this as delta theta. That means the change in the two angles that I see. Okay, so that's what I have. Okay, so this is the equation actually, right? Okay, for a source sink pair, okay, that's separated by distance L here. Alright, now the question is this. We say, right, for a doublet to happen, okay, the L has to be very, very small. Okay, so that means, right, we must be able to quantify what is this delta theta equals to. Okay, so how do we do that? Alright, so the first thing is this. We can now assume, okay, that for this diagram that I've drawn for you, okay, I assume that my L is so small, okay, that even if I multiply by the source of the sink strength, okay, the value is still a constant value. Okay, that means, right, L doesn't change the behavior anymore, okay, because it's so small that we see. Alright, but for understanding's sake, right, I still have to draw a certain value just to show to you, okay, that source and sink is so close, but still defined by a certain value of L that we can calculate. So what I've drawn for you here, okay, is something like a right angle triangle, okay, for some reason also. Because from the source to point P and from the sink to point P, there are some distances, okay, they cannot be the same distance, right? A source and a sink cannot be together, that means they cannot be on the same point, but they can be very close together. Understand what I'm saying? Okay, therefore, right, if you can think about this, right, my R and B right, actually can become almost the same value, but they cannot be the same value. Right, because if they are the same value, that means my source and sink is on the same location. So that cannot be the case, right? So therefore, right, there must be some relationship between my R and my B value here. Okay? So take note, what I'm trying to do here is this. Because in the previous slide, right, we have this delta theta here. That means a change in my source and sink location. So this delta theta really, right, is just this here, my d theta. Because from a delta theta, okay, it changes into a d theta here. Okay, so I can do this into a math form. Okay, but the definition is this: if L goes to become very small, okay, L multiplied by the source or the sink strength is just a certain constant value. Okay, so for a doublet, right, instead of writing this inverted V, okay, to define the strength of the doublet, we use as kappa or kappa, right? Okay, so kappa is L of the inverted triangle here. Is there any copy here? Okay, so now we are still at the point of just defining the strength of the doublet. Okay, so in the question, right, okay, if you are given kappa, right, you should know that that's only just for a doublet. Okay, so what we need to do, right, again, right, is to be able to define the string function and the velocity potential, okay, for a doublet. Okay, so how do we do that? Alright, so there are a few things that we can do to assume. Okay, as I said, right, we can have this triangle here, or a triangle that has got this value here. So R and B, okay, like what I say, R just now, right, is the distance from the source to P. B, right, is the distance from the sink to point P. P is just an arbitrary value, arbitrary point. Okay, that means P can change anywhere I want to go. Okay, but that's just that I introduced my R and B to you. Okay, so R and B are just distances from your source or your sink to point P. Okay, so what I've done, right, is the only way for me to link between the source and sink, okay, is to introduce this value of A here. Okay, that means how is A, what's the closest distance from this point here, okay, to my R distance here. Okay, so let A be the perpendicular distance from sink to the point R here. Okay, so there are two assumptions that we make. The third, more important assumption is this. Okay, we are looking at small angles approximation. Okay, what is small angle approximation? Do you understand? If I have sine theta, right, it becomes theta. Correct? So if I have sine d theta, it becomes a d theta here. Okay, so why is it a small angle approximation? Because, right, we are assuming that source and sink is very, very close to one another. So therefore, right, this angle actually is very, very small. So that's why this assumption is valid here. Okay, so now let's try, okay, this is my L, this is my A. Okay, how is A and L related to one another because of theta? Anyone? Why is sine theta equals to, there's a theta, what is sine theta equals to?
You have me text something on the group chat.
Right? Sine theta equals to opposite over hypotenuse, so sine theta equals to A over L.
On the
So that means my A will be equals to L sine theta.
on the lab report, the group chat.
Okay? Now,
Fluids
remember what I say? R is
Remind
distance
them
from
to
source
stay
to
back after
P
this, we
and
do
B is
the-
distance
we
from
do the
sink to P, right? Now, how is R and B going to be related? What is B equals to? You look from here. Is B equals to R? Cannot be, right? If B equals to R, means source and sink is on the same location, so it cannot be. Therefore, right, you can see from here, right, from this diagram, my R actually is bigger than B. Okay? So that means, right, if they are almost so close to one another, right, I can say that my B actually just R minus my L cos theta. Okay? Now, where is L cos theta? Okay, so this is my L cos theta here. Alright, the last thing that's important is this. How is d theta? Okay, you look at this triangle here. I got a A, I got a B, Okay, how is d theta related to a and b? Because this is a right angle triangle, right? Okay, so that means what? My sine d theta will be equals to what? Opposite over hypotenuse, which is a over b. Okay, but because it's a small angle approximation, okay, I don't need the sine anymore. So it just be d theta equals to a over b here. Okay, now this is very important to me because I got one equation in terms of a, one equation in terms of b, and then one equation that's got a and b here. So that means, right, I can change now my a and b in terms of this equation here. Correct? Okay, so if I put a as L sine theta, if I put b as r minus L cos theta, okay, what do I have? I have my d theta equals to L sine theta over r minus L cos theta. Okay, we are almost there for the doublet, okay? Just hang on for a few more minutes. Okay, so since at the start, right, we mentioned that our stream function is a superposition of the two values that we have, the source and the sink. Okay, I further change this to a d theta, right? Okay, that means, right, I can now sub in this d theta, okay, with my L sine theta and my r minus L cos theta here, correct? Okay, so that means I can write this down. Okay, what's the stream function equals to for L to be very close to equals to 0? Okay, now this is very simple already. The reason is because of this. If, right, I assume that L becomes very, very small and close to 0, okay, my equation will just be simplified to this equation here. Okay? So, what is this kappa here? Kappa is equal to what? Okay, your inverted B multiplied by L. That's why this one, this source strength multiplied by L gives you my kappa here. Okay, so in a sense, right, because my L becomes very small, right, almost to 0, this term will be cancelled off. Alright, that's why I have this equation here. Yeah, I mean you can see from here. So my inverted V, right, multiplied by L is my kappa. Okay, this L cos theta, because L goes to 0, okay, this L cos theta will be 0 already. That's why I only left with an R at the bottom. Okay, so therefore, right, the definition for my string function for a doublet is equal to this value here. Okay, please remember this. Are we okay? Okay, so by the same token, okay, we can do the same thing for my velocity potential. Okay, so this is the final equation that we have also. Okay, so in the previous equation, okay, your stream function is minus k sine theta over 2 pi r. Okay, for the velocity potential is k cos theta over 2 pi r. Okay, so the thing is, right, there was a question I think in the exam, right, where you are given the stream function for your doublet, right? You're supposed to prove the velocity potential. Okay, that means how do I get to these values here? So I thought perhaps, right, it's better that I show this to you. Okay, how you actually get the answer. Okay, so if, right, you can remember this relationship here. Okay, that means my VR, my V theta, how is it related to my stream function and velocity potential? Like what I mentioned to you, right, if I know one value, I can find the other already. Okay, so am I right to say, right, if my radial velocity is 1 over r del psi over del theta, and it's also equal to del phi over del r, what can I do is I can equate this equals to this, correct? Okay, so I can do the same thing like what I mentioned here. So, in fact, right, when I do that, I'm just doing a very simple integration already. Okay, because del phi over del theta, right, if you have this equation here, okay, once I want to find my velocity potential, how do I do it? What do I have to do? Anyone? I just got to integrate, right? Okay, so if I integrate this, what do I have? I will have this equation here. K cos theta over 2 pi r. Okay? What's the reason for this? Because I'm integrating so I'm just doing this partial integration of my del phi over del r over this. So that means, right, to me, right, my cos theta is a constant value, right? So I don't integrate. That's why my cos theta stays the same. But here is a minus 2, right? Because it's r minus 2. If I integrate, I get what? R minus 1, right? Over minus 1. So the minus sign will cancel out. That's why you have a positive here. Alright, so you have a 2 pi r here. Is anybody lost here? I hope not. Okay. So the question is, right, what is this f theta equals to? If I want to find what is this f theta here. Alright, so I can do the same thing now, okay, for the other side of the equation in the previous slide. Okay, I can actually now do a partial derivative, okay, in terms of my theta not theta 1. Okay, now if I do this, right, okay, then therefore, right, I can change my cos into my sine if I want. Okay, so that's why you have a sine here. Okay? So if I now also have this equation here, my delta psi over delta theta, right? Okay, I can actually then change this into this equation here. Okay? So what's the reason for doing this? I'm trying to show to you, right, if you know for one stream function, okay, you can do the same math functions, right, to get for your velocity potential also. It's vice versa, okay? That means what if the question gives you the stream function of the velocity potential of a doublet, okay? You can do the same thing to find the stream function also. Okay? Based on whatever, based on the relationship that I've established at the start already. Okay? So anyway, once you do this, right, you realize that your f prime theta is equal to 0. Okay, so if f prime theta is 0, right, it just means, right, that f theta is a constant. Okay? So therefore, right, the final answer that I have will still be this. Okay? Your phi will just be equal to k cos theta over 2 pi r. Okay, so if I can, right, I urge you guys next semester, right, if you ever come back to this slide here, be able to do the change. That means if I given the stream function, okay, how do I find the velocity potential? Or if I given the velocity potential, right, how can I find the stream function? Okay, as a mathematics exercise. Okay, it's quite important for you guys. Okay, so I've covered uniform flow, source, sink, right, and then a doublet. Okay, the last thing I want to cover for today is just the last one, okay, which is your vortex. Okay, so vortex is something that we have covered before already, which is last week. Okay, so a few important points that I want to re-emphasize. Okay, so for vortex flow, okay, please remember your VR is equal to 0. Okay, because, right, it's a pure tangential flow. Okay, so the thing is spinning about a certain point. Okay, that's why there's a certain v theta. Now, what's your v theta equals to? Your v theta equals to k over r, right? Now, what is k equals to? K is your vortex strength, correct? Okay, so I've derived for you, okay, I mentioned to you, right, that the vortex strength is equal to negative of your circulation over 2 pi. Yeah, that's where I introduced the tau also to you. Okay, negative, positive doesn't really matter. Okay, for us, right, if it's a clockwise motion, consider as a negative value. Right, anti-clockwise is positive. Okay. And when we went through the potential vortex or the vortex flow, okay, it was where we talk about Cartesian to polar form. Okay, so we must be able to change from Cartesian to polar form. Okay, so these are nothing new here. Okay, I mentioned this to you before already. Okay, so other things that is important is this. I went through the definition for you, okay, for how to find the circulation, right? Because if you look from this slide here, okay, there's still one unknown that we don't know, okay, which is my tau. Okay, what's the circulation strength? Okay, so I went through this thing where I talk about this Stokes theorem. Okay, I said it almost every other week. Okay, what's the meaning of Stokes theorem here? So there's another equation that we can use. That means if I want to look at the vorticity and the area, we can do the same thing also. But for now, right, if I base on this equation, okay, I can actually find out what is my velocity component that I want. Okay, so if you look at this, right, because this is a vortex flow, what is this V equals to? VR or V theta? Or both? VR, theta or both? But what is your VR equals to for this flow? 0, right? Therefore my V, right, can just be equals to my V theta. Alright? Now what is this dl equals to? What's the length scale equals to? Anyone? How is this flow going in a circulation motion, right? So what's the length scale equals to? It will be equals to my 2 pi r, right? Because if I'm the flow, right, my flow is moving in a circulation motion, right? So the circumference becomes the length scale that I mentioned. That's why it's my 2 pi r. Okay, so that means, right, I can find my V theta, okay, if I given the circulation strength, okay, as minus tau over 2 pi r. Okay, now why am I doing this again? Okay, as per all the other flows that I've gone through, okay, what I'm trying to do, right, is to find the stream function and the velocity potential. Now, why do I want to do that? Okay, I want to do that because I can superimpose all the different flows together. As I mentioned to you, right, the only way for me to superimpose the different flows together is through the stream function of the velocity potential. That's why there's a need for us to use all these different flows that we have, okay, and derive the stream function for each of them. Yeah. Okay, so now if I know V theta, right? Okay, we know how is V theta related to my stream function, okay, and also how is my radial velocity related to my stream function. But because for vortex flow, the radial velocity equals to 0, okay, so I cannot use this term to get my answer. Okay, but since, right, I know my V theta is some value here. Okay, therefore, right, I can then use this and then I can do the integration. Right? Now, if I integrate this, what do I have? What do I have if I integrate this value? My stream function is equal to what? Anyone? I'll get this tau over 2 pi times ln r. So you understand why is ln r, right? Okay, because I'm integrating 1 over r with respect to r. Okay? Now, why do I put an f theta here? It's a function of theta, right? But I still need to put it down because this is a partial derivative. Okay, so I need to do my due diligence, right, to make sure that I can find what is this f theta equals to, in order to find. Okay, now from here, we know, right, the partial derivative of my stream function with respect to theta is equal to 0. Therefore, my f prime theta equals to 0. And because my f prime theta equals to 0, okay, my f theta is a constant value, which I don't have to consider. So therefore, right, the stream function for a potential flow or vortex flow is equal to this. Okay, please highlight this, okay, this is very important also. So that means, right, in the exam, if ever, right, you are given a value of stream function that has got tau here, okay, straight away, right, you must know that this is for a vortex flow. Because the only flow, right, that has got circulation is your vortex. Any other flow, right, whether it's a uniform flow, a source, a sink, or doublet, it's not circulatory, therefore there's no circulation. Okay? The moment you see that there's a circulation value here, it simply tells you, right, that it's a vortex flow. Okay? Okay, so I think you can anticipate what's the next step I want to do already. I've given you the stream function. Okay, so the next step obviously I must find is what? My velocity potential. Alright? So now I have the stream function. Okay? And I also know that my V theta has got a certain value because VR equals to 0. Okay, so with this, right, okay, I can actually sub in my sine, okay, with this value here, right, tau over 2 pi times ln r. So if I put this down, right, I will have this equation here. Alright, so that means I can then find what is my velocity potential equals to. Okay, so if I integrate this, very simple, right, I get this answer here. Okay, so GR is just a function of r, function of the radius I must find. So again, right, okay, we must make sure that we find that VR is equal to 0. Therefore, your G prime R equals to 0. Therefore, GR is a constant. We can cancel this off. Okay, so that means my velocity potential, right, is just equal to this value. Okay, so this is another box that I think you should remember. I just want to go through one last flow behavior. Okay, then I think I will stop today. Okay, so we have mentioned 5 different flows, right? Okay, very simple flows: uniform flow, source, sink, doublet, and your vortex. Okay, they can all be expressed in terms of their either U or V or VR or V theta, right? But as I said to you guys, right, we cannot use these 4 different values, right, to add up together the flows. The only way we can add up the flows, right, is where we change that into stream function or velocity potential. Alright, so for one example, right, is this what you have done in your lab. Okay, so if you recall what I said just now, okay, because of the Laplace equation, right, okay, the total stream function is a summation, just a simple summation of all the different flows that we have. Okay, so as an example, what we can do, right, is that let's say you have a uniform flow that's passing through a source. Okay, now what do I see here? Okay, so that means, right, if I only have this flow and this flow, I can add this up, but I cannot add the velocity up. Okay, because velocity values are different. Okay, and they are vectors also. So the better way for us to do this, right, is based on the definition here, the stream function definition here, where you can superimpose different flows together. Okay, now if you look at this, right, this is a uniform flow, okay, and it's in pure axial direction. Okay, that means, right, I know that I can then have this equation here. UR sine theta, okay, represents the polar coordinate system for the uniform flow. Okay, this is for the source flow. Alright. So I can do the same thing, right? Instead of having the stream function, I can actually add up my velocity potential if I want to. Okay, so it depends on the question, as I said. Okay, so what is given to you, you can do the addition together. Okay, or what is required of you, right, you can actually derive the other variable. Okay, so if you've done the lab, right, you will know that uniform plus source, actually you get this sort of a shape here. Okay? If I add these two up, okay, really it's just addition here. Okay, and this is what you see as a ranking half point. So essentially, right, this is just like a flow over a bluff body. Okay, you have a certain stagnation point, okay, but the flow will just go past the source, right? Is there any lift in this flow? Do you think there's any lift generated here? There will not be any lift generated here, okay? Okay, so let's do a little bit of analysis for this case, okay? So this is a typical flow behavior, okay? You have uniform plus source. Sometimes you can have a uniform plus doublet also. Alright, eventually you can have a uniform plus doublet plus vortex. Okay, but the simplest of the superposition, right, is this uniform plus a source. Alright? Okay, so if you think about this, right, this is the stream function, okay, for this flow behavior. Okay? Now, again, right, we can find a few things. Okay, because we know how is our radial and our tangential velocity related to our stream function. Okay? So very simple, right? We can actually find what is my v theta equals to. Okay, and what is my v radial equals to? Okay, now any problem with these two? Understand what I'm doing here? Because v theta, right, is minus del psi over del r. Okay, so I just do a very simple differentiation. I get my u sine theta. Okay, now let me just go back to the previous slide. You can see from here, right, this term here has got no r value, right? So if I do a partial derivative in terms of radius, this is a constant value. Right? So the only thing that differentiates is my ur sine theta. Okay, if I differentiate ur sine theta with respect to r, I will get my u sine theta. Okay? Now why is this a negative sign? Just because there's a negative as a definition here. Okay? I can do the same for my radial velocity. Okay, now I'm differentiating with respect to what? For radial velocity. With respect to theta, right? Okay, so if you go back to the previous slide, you can see that if I do respect to the theta, okay, this has got theta, this has got theta also. So I must do for both sides here. Alright? That's why I have these two terms here. My sine will become my cosine. Okay, and this will be 2 by r. Alright? Okay, so you can see from here, right? Just now we mentioned, remember, a source flow or a sink flow, what is equal to 0? VR or v theta equals to 0. For a source flow or sink flow, what is equal to 0? Your radial or tangential velocity. Your tangential velocity equals to 0, right? But you can see, right, now if I superimpose the two flows together, my v theta will not be equal to 0 anymore. Okay, because there's a certain uniform flow values there. Okay, so what does this mean to us, right? If I do a little bit of analysis here, which I think is quite helpful for your lab, so please listen. Okay, so whenever a flow hits against something, right, okay, there's always a stagnation point. Okay, now a stagnation point, right, is always where velocity equals to 0. Okay, so in this case, right, as my flow comes to very near to the source here, okay, at the point B here, okay, we can assume that there's a stagnation point here before the flow starts to deviate upwards away from the source. Yeah. Okay, so that's why I say, right, this is just like a flow over a black body. Okay, so at the leading edge here, okay, at the front point of the source here, okay, there will be a stagnation point. Okay, that means, right, if I say velocity equals to 0, what does this mean? It means that, okay, the stagnation point, my VR and my V theta has to be equal to 0. Agree? Okay, because if VR is not 0 or V theta is not 0, right, I cannot have a stagnation point. Stagnation point is a total velocity. Therefore, my VR and my V theta, right, must be equal to 0. Okay, this is very important to me because I can find two things. I can find the theta value where there's a stagnation point. I can also find the R value, okay, where there's a stagnation point. Okay, so if you think about this, right, I got V theta and VR here. Okay, I can then put in the two